says, so you have Jake again, and he's on a river. So let's say you have like a river. This is like your river, and he's riding a boat on he's paddling upstream, and so let's draw his like boat. So this is Jake, right? And let's say like the current, so the water is going to have a current, right? So let's say like the current is going to like go like this way. So this is the current. And Jake is going to be riding in his boat, and he's also going to be traveling at some speed. So we're given paddling upstream, Jake can travel at a rate of 2 miles per hour relative to the shore. So when a question says like upstream or downstream, those are important terms. So it turns out like these questions about a person on a river or like a person like on an airplane and there's like a wind or something, those are very typical problems with distance, rate, and time. So if you see like the word upstream, that just means if a person is traveling upstream, that just means that they are traveling in the opposite direction of the current. So if the current is going to the right, then if the person is traveling upstream, then they're going to go to the left. They're going to go in the opposite direction of the current. And we're given that upstream, it's going to be 2 miles per hour. And we're given if he travels downstream, downstream just basically means he goes in the direction with the current. So this represents upstream, and this way would represent downstream. And we're given when Jake goes downstream, he's going to travel at 10 miles per hour. And we want to know what is Jake's speed in still water. So still water is another like common term. Still water just means when the current is 0, basically. Like if let's say you're in water and there's no current at all, how fast would you be moving? So how you would solve this problem is you don't actually have to use distance equals rate times time for this problem. This is kind of an example of a relative velocity problem. So the idea is we can let C represent the speed of the current, right? And let's let like R represent Jake's speed in still water. So we have two variables, R and C. So when Jake is traveling upstream, he's going to be traveling upstream at a rate of R, but the current is going to be pushing him back at a speed of C, right? So Jake is trying to travel at a speed of R, but the current is dragging him back at a speed of C. So the net velocity, or the net speed, basically, like the net rate, is going to be R minus C. Since he's going at a speed of R, but the current is pushing back him with the speed of C. And we're given this is equal to 2. And for the downstream equation, downstream is when Jake is going with the current, when he's traveling in the same direction as the current. In this case, the current is going to kind of help him travel faster. So he's going to travel at a rate of R normally, but then the current, which has speed C, is going to like push him forward. So it's going to push him faster, and it's going to make him travel at 10 miles per hour. And we basically want to find what is the value of R. R represents his speed in still water. So we can solve this pretty easily by using elimination for this system of equations by like adding the two equations. So on the left side, you would have R minus C plus R plus C, that is 2R. And on the right side, you have 12. So dividing by 2 on both sides, you would get that his speed is 6 miles per hour, which is our answer.